It's like almost looks like a cone structure that's emanating from the surface, like surrounded by a circle. Like what's that? A groundbreaking discovery has just emerged from Proxima b, one that has left astronomers searching for answers. Recent infrared data from the exoplanet has revealed an unexpected structure, something massive and unlike anything seen on a rocky world before. It does not resemble any known planetary formations, and its unusual characteristics are raising serious questions about what exactly has been detected. The discovery, astronomers have been studying Proxima b for years, searching for signs of geological activity, atmospheric composition, and potential surface features. But nothing could have prepared them for this. Using a combination of infrared telescopes and computational models, researchers have identified a large-scale anomaly on the planet's surface, an irregular formation with a thermal and reflective signature that stands apart from the surrounding terrain. This anomaly is not a simple surface variation. Its heat retention properties and light reflection patterns are significantly different from what would be expected of a rocky exoplanet orbiting a red dwarf star. The structure appears to absorb and emit heat in an unusual manner, and its reflectivity suggests a composition that does not match typical planetary geology. Confirmed observations. Light analysis has detected a concentrated region of heat-retaining material vastly different from the rest of the planet. The formation's temperature readings are inconsistent with any known geological feature, challenging existing models of rocky exoplanets. The reflectivity in this region is unusually high, raising questions about whether the surface contains materials with unexpected optical properties. No known planetary process fully explains the combination of these anomalies, leaving astronomers to reconsider what might be hiding on the surface of Proxima b. With multiple observatories confirming these findings, scientists are now intensifying their efforts to analyze and understand what this structure could be. Is it a previously unknown planetary phenomenon, an exotic mineral deposit, or something entirely different? The search for answers is just beginning. With the discovery confirmed, scientists are now focused on analyzing the data to determine what this anomaly actually is. Observations from multiple telescopes have revealed three distinct characteristics that make this structure unlike anything previously seen on a rocky exoplanet. Three key anomalies that don't match standard models. 1. Unusual thermal readings. Infrared measurements revealed that this structure has an extreme temperature contrast compared to the surrounding landscape. While most planetary surfaces cool down predictably after exposure to their star's radiation, this anomaly retains and releases heat in a way that does not align with known geological processes. The temperature fluctuation suggests that the material in this region has properties that are fundamentally different from the rest of the planet's crust. 2. Reflective properties are inconsistent with planetary surfaces. Visible and infrared light measurements show that the anomaly reflects light at a significantly higher rate than expected. This could indicate the presence of an unusual mineral composition or even a highly reflective surface material. Scientists are investigating whether the structure contains elements that are rare in rocky planets or if its composition is something entirely unfamiliar. 3. Geological simulations fail to explain it. Planetary models have been run to determine whether natural processes could have produced this structure, but so far they have failed to provide a clear explanation. No known geological activity, such as volcanic deposits, impact craters, or tectonic formations, accounts for the anomaly's shape, size, and composition. This lack of a natural explanation has made the discovery even more intriguing, prompting astronomers to explore alternative possibilities. With these unexplained factors in play, researchers are now intensifying their investigations, hoping to uncover what this structure represents and whether it challenges our understanding of planetary formation. With the anomaly confirmed and early data revealing inconsistencies with standard planetary models, the focus has now shifted to understanding exactly what this structure is. Astronomers are conducting a series of advanced tests to analyze its composition, origin, and potential implications for exoplanet science. Ongoing scientific investigation, spectral analysis for composition identification. One of the most critical steps in the investigation is spectral analysis, which breaks down light reflecting off the anomaly to determine its chemical makeup. By comparing these spectral signatures to known elements and minerals, scientists hope to identify what materials are present and whether they are common in planetary geology or something unexpected. Cross-referencing with other exoplanets to understand whether this is a unique case, astronomers are comparing Proxima b's anomaly with surface features observed on other rocky exoplanets. If no similar structures are found elsewhere, it could suggest that this is a rare or even unprecedented planetary phenomenon. Ground-based radio telescopes scanning for energy signatures. In addition to visible and infrared studies, astronomers are using radio telescopes to scan for any emissions coming from the location. While planetary surfaces don't typically emit strong radio signals, an unusual material composition or energy trapping process could produce detectable frequencies. The discovery has caught the attention of leading space agencies, which are prioritizing new observational campaigns to study Proxima b in more detail. Ground-based observatories are refining their measurements to determine whether the structure changes over time. Scientists are exploring whether advanced space telescopes could be used to capture high-resolution infrared images of the anomaly. New planetary models are being developed to test whether extreme stellar conditions near a red dwarf could produce formations previously thought impossible. While no conclusions have been drawn yet, the next wave of observations could provide groundbreaking insights into the nature of Proxima b's unexplained structure. With new data pouring in, scientists have begun narrowing down possible explanations for the anomaly. While no definitive answer has emerged, three leading theories are currently being explored. Each one challenges existing models of planetary geology and could reshape how we understand rocky exoplanets. The first theory suggests this is an unidentified geological structure, a type of planetary formation never before observed. However, this theory is already facing challenges. The structure's heat retention is far greater than any known rock formations, which typically cool at a predictable rate. Its reflective properties suggest a surface material that is highly unusual for a rocky exoplanet. No existing planetary models predict the formation of such a structure under Proxima b's conditions. If this explanation holds, it would require rethinking how extreme environments near red dwarf stars shape planetary surfaces. The second possibility is that the anomaly represents a massive deposit of an exotic mineral or metal that is rare or unknown in planetary science. Some clues support this idea. The high reflectivity and thermal properties could indicate a metal-rich surface, possibly formed by unique geochemical processes. Proxima b is exposed to intense stellar radiation, which may have influenced the chemical makeup of its crust. If confirmed, this would provide the first direct evidence of large-scale metallic or heat-retentive mineral formations on an exoplanet. However, scientists have yet to find a direct match between the spectral readings from Proxima b and known mineral compositions, leaving this theory inconclusive. The third and most intriguing possibility is that this structure represents a completely new type of planetary feature, something unseen in our studies of exoplanets so far. This would mean Proxima b is home to geological or atmospheric processes that have not been accounted for in current models. No other exoplanets observed to date have shown a formation with this specific combination of characteristics. If this anomaly is not explained by standard geology or mineral deposits, it could signal an entirely new planetary process. The discovery could force a re-evaluation of how rocky planets form and evolve under extreme stellar conditions. At this stage, no single theory fully explains all aspects of the anomaly, leaving astronomers with more questions than answers. The next step is to collect even more data and refine these hypotheses further. With the anomaly still unexplained, astronomers are ramping up efforts to gather more data and refine their understanding of what they are observing. Over the next months and years, new studies and advanced telescope observations will be critical in determining whether this is a natural geological feature, an exotic mineral deposit, or something entirely unknown to planetary science. Ongoing and upcoming scientific efforts include additional telescopic observations. Ground-based observatories will continue monitoring Proxima b, focusing on detailed spectral analysis and infrared mapping to track temperature shifts over time. These observations will help determine whether the anomaly changes due to stellar activity or other external influences. Second, polarimetric studies to assess composition. Polarimetric imaging, a technique that measures how light interacts with surface materials, will be used to determine whether the structure is made of crystalline or metallic elements. This could provide the key to identifying its composition and origin. Third, reviewing historical research. Scientists are combing through past exoplanet studies to see if similar anomalies have ever been recorded but overlooked due to technological limitations. If similar structures exist elsewhere, it could provide valuable context for understanding the formation on Proxima b. Future space missions and advanced telescopes include first, space telescope observations. Evaluations are being made whether advanced space telescopes can be directed toward Proxima b to provide high-resolution infrared imaging of the anomaly. If approved, these observations could offer unprecedented detail about its structure, thermal behavior, and potential chemical composition. Second, next-generation space telescopes. Beyond current capabilities, future observatories, such as upcoming extremely large telescopes and planned exoplanet-focused space missions, may be able to provide even more precise data on the anomaly. If it remains unexplained, it could become a priority target for the next era of space exploration. At this stage, astronomers are certain that Proxima b's surface holds something truly unique. The question now is whether upcoming studies will provide an answer, or if this discovery will redefine how we study exoplanets altogether. While scientists are making progress in studying the anomaly on Proxima b, several major challenges remain. One of the biggest obstacles is the limitation of current telescopes. Ground-based observatories, despite their advanced instruments, can only provide a certain level of detail due to Proxima B's distance and the interference caused by its host star. Even space-based telescopes may struggle to achieve the resolution needed to reveal surface-level details with certainty. This makes it difficult to determine whether the anomaly is a distinct structure, an unusual mineral deposit, or something entirely different. Another challenge is the lack of comparable data from other exoplanets. So far, no similar structures have been observed on any other rocky worlds, making it hard to establish patterns or find an existing explanation. If this formation is unique, it suggests that Proxima b has undergone planetary processes that we have yet to understand. Scientists are searching through previous studies to see if any overlooked anomalies might provide additional context, but as of now, Proxima b's irregularity remains an outlier. Adding to the difficulty is the highly active nature of the red dwarf star that Proxima b orbits. The star produces frequent solar flares, which not only bombard the planet with intense radiation, but also interfere with observational data. These bursts of energy make it harder to isolate signals from the anomaly, and could even be affecting the structure itself in ways scientists have not yet accounted for. Understanding whether the formation is stable or changes over time will be crucial in determining its nature. To overcome these roadblocks, astronomers are refining their methods. Future space telescopes, equipped with more advanced imaging capabilities, will be needed to capture higher resolution data. Scientists also plan to conduct deeper spectral analysis to pinpoint the exact chemical composition of the anomaly. Additionally, long-term monitoring will help determine if the structure evolves or remains static, providing key insights into its origin. With these steps, researchers hope to finally uncover the truth about this unexplained feature on Proxima b. The discovery of this anomaly on Proxima b is more than just an isolated mystery. It has the potential to reshape our understanding of exoplanets and planetary science as a whole. If this formation turns out to be a geological structure unlike anything found in our solar system, it could challenge existing models of planetary evolution. Current theories suggest that rocky exoplanets should follow predictable patterns of surface composition and temperature distribution. Yet Proxima b is showing characteristics that do not fit these expectations. If the anomaly is a large metallic deposit or an exotic mineral formation, it could indicate that planets orbiting red dwarf stars develop in ways we have never considered. Beyond geology, this discovery raises questions about the role of extreme stellar environments in shaping planetary surfaces. Proxima b is subjected to intense radiation and stellar activity, which could be influencing the composition of its crust in unexpected ways. If scientists determine that this structure is a result of the harsh environment, it may provide valuable insights into how planets around red dwarfs, some of the most common stars in the universe, form and evolve. This could directly impact the search for habitable worlds, as understanding planetary composition is crucial in assessing whether a planet has the right conditions to support life. Additionally, this anomaly highlights the need for more advanced observational tools. The limitations of current telescopes make it difficult to draw definitive conclusions, reinforcing the importance of upcoming space missions designed to study exoplanets in greater detail. Future telescopes, such as extremely large ground-based observatories and advanced space telescopes, may provide the resolution needed to unlock the secrets of Proxima B's surface. In the long term, this discovery could influence the selection of targets for interstellar exploration. If the anomaly remains unexplained, it may become a high-priority location for future space probes or even theoretical missions aimed at sending spacecraft to nearby star systems. At its core, the discovery of an unexplained structure on Proxima b reminds us that planetary science is still in its early stages when it comes to studying exoplanets. Every new observation adds another piece to the puzzle, and in some cases, challenges what we thought we knew. Whether this formation turns out to be a new type of geological feature, an exotic mineral deposit, or something even more unexpected, one thing is certain. Our understanding of distant worlds is about to change. The discovery of this anomaly on Proxima b is one of the most intriguing ever detected on an exoplanet. Despite extensive analysis, scientists still don't have a definitive explanation for what this structure is, and new research is already underway to solve the mystery. Astronomers are preparing for more advanced observations, new studies are being published, and space agencies are considering future missions that could provide a clearer picture. The search for answers is far from over. Stay updated as this story unfolds. Could this discovery reshape our understanding of planetary science? Will upcoming telescopes finally reveal the true nature of this structure? Be the first to know when new findings are released. Subscribe now for real-time updates on the latest space discoveries and cutting-edge research into the unknown. Peer into the unknown. The enigmatic structure on Proxima b continues to defy conventional explanations, pushing astronomers to consider radical new possibilities. Recent observations from next-generation spectrographs have detected unexpected quantum signatures in the anomaly's reflected light, suggesting the presence of materials with exotic crystalline structures not naturally occurring in our solar system. Some researchers speculate this could indicate extreme pressure-temperature conditions unlike anything encountered on terrestrial planets, possibly created by Proxima Centauri's intense gravitational tides acting on the planet's crust. Cutting-edge simulations now suggest the anomaly might represent a new class of planetary feature, a stellar-forged geological formation. These models propose that repeated megaflares from Proxima Centauri, some emitting X-ray bursts 1,000 times stronger than our Sun's most powerful flares, could be superheating surface materials to create previously unknown mineral phases. The European Southern Observatory's latest adaptive optics data reveals the structure's thermal emissions pulse, in rhythm with the star's 83-day activity cycle, hinting at a dynamic relationship between the anomaly and its host star. The scientific community is particularly intrigued by recent findings showing the structure's albedo varies dramatically across different wavelengths. Preliminary analysis of these spectral fingerprints suggests the possible presence of metastable metallic alloys that could only form under continuous stellar bombardment. This has led to controversial theories about stellar alchemy, where a red dwarf's relentless radiation transforms surface elements into exotic compounds over billions of years. New evidence from radio interferometry has added another layer to the mystery. The structure appears to be surrounded by a faint but persistent low-frequency radio halo, a phenomenon never before associated with planetary surfaces. While some researchers attribute this to trapped plasma in unusual surface formations, Others cautiously suggest it might indicate previously unknown electromagnetic interactions between a planet's crust and its magnetosphere under extreme stellar conditions. The upcoming deployment of space-based mid-infrared observatories promises revolutionary insights. These instruments will map the anomaly's thermal inertia with unprecedented precision, potentially revealing whether the structure contains heat-conducting channels or unusual energy distribution patterns. Simultaneously, breakthroughs in quantum-enhanced spectroscopy may finally decode the structure's chemical signature, possibly identifying never-before-seen mineral configurations. This extraordinary feature on our closest exoplanetary neighbor continues to challenge fundamental assumptions about planetary science. As observational technology approaches the capability to resolve surface features on exoplanets, Proxima B's anomaly stands as both a tantalizing mystery and a beacon for future exploration. The structure's very existence suggests we may need to completely revise our understanding of how terrestrial planets evolve around the universe's most common stars, with profound implications for the search for life beyond Earth. Every new observation brings us closer to potentially rewriting the textbooks on planetary formation, while simultaneously revealing how much we still have to learn about the alien worlds in our cosmic backyard. Recent breakthroughs in exoplanet atmospheric modeling suggest the Proxima b anomaly may be interacting with the planet's thin hydrogen envelope in unexpected ways. Advanced climate simulations now show the structure creates measurable distortions in atmospheric circulation patterns, generating localized weather phenomena unlike anything observed in our solar system. Some researchers speculate this could represent the first evidence of stellar wind sculpted topography, where a red dwarf's persistent particle bombardment physically reshapes planetary surfaces over geological timescales. Cutting-edge quantum mineralogy studies propose the structure might contain ultra-dense polymorphs of common elements forged under Proxima b's extreme surface pressures. Laboratory experiments recreating the planet's estimated 10,000 G surface gravity have produced previously theoretical forms of iron and silicon that exhibit similar thermal and reflective properties to the observed anomaly. These hypercompressed materials could explain the structure's ability to retain heat while maintaining high reflectivity, properties that defy conventional geological understanding. The anomaly's radio emissions have taken on new significance with the detection of synchronized pulsations matching Proxima Centauri's magnetic cycles. This has led to radical proposals about planetary-scale piezoelectric effects, where the immense tidal forces acting on Proxima b's crust generate measurable electromagnetic signatures. If confirmed, this would represent an entirely new category of planetary electromagnetic phenomena, potentially rewriting our understanding of how terrestrial planets interact with their host stars. New analysis of decades-old astronomical data has uncovered something startling: possible evidence of similar anomalies on other red dwarf exoplanets. While less pronounced than Proxima b's feature, several M-dwarf orbiting worlds show infrared signatures that may represent smaller versions of the same phenomenon. This revelation has sparked urgent calls for a systematic survey of nearby exoplanets, with some scientists suggesting we might be witnessing the emergence of an entirely new classification of planetary feature specific to high-energy stellar environments. The upcoming generation of space telescopes promises revolutionary insights. Advanced coronagraph systems will soon allow direct imaging of Proxima B's surface, potentially revealing whether the anomaly stands in topographic relief or represents a subsurface feature. Meanwhile, developments in neutrino spectroscopy could provide unprecedented information about the structure's density profile, possibly determining whether it extends deep into the planet's mantle or crust. Perhaps most intriguing are new theoretical models suggesting the anomaly might be a dynamic rather than static feature. Some researchers propose it could be a visible manifestation of ongoing planetary differentiation, where Proxima B's interior is gradually reorganizing under intense stellar heating. This would make it the first observed example of real-time planetary evolution, offering a living laboratory to study processes that on most worlds occurred billions of years ago. As the scientific community mobilizes to solve this mystery, one thing has become clear. Proxima B's anomaly represents more than just a planetary curiosity. It challenges fundamental assumptions about terrestrial planet formation and evolution, suggesting that worlds orbiting red dwarfs may develop along radically different geological pathways than previously imagined. With each new observation and analysis, we're not just learning about one strange feature on a distant world, we're potentially uncovering an entirely new chapter in planetary science. The anomaly's gravitational signature has recently revealed another layer of mystery. Ultra-precise Doppler measurements detected subtle perturbations in Proxima B's orbit that suggest the structure may contain anomalously dense material concentrated in a relatively small area. This has led to startling proposals that the feature could be a surface manifestation of a massive metallic upwelling from the planet's core, potentially caused by extreme tidal heating from its red dwarf host. Such a phenomenon would represent an entirely new category of planetary volcanism, unlike anything in our solar system. Breakthroughs in nanotechnology have enabled new analysis of the structure's light-scattering properties. Scientists have discovered the anomaly reflects polarized light in complex patterns that suggest its surface contains perfectly aligned crystalline structures at macroscopic scales. This degree of natural crystalline organization